So first, before I start, exam one is a week from this upcoming Friday. No, this upcoming Wednesday. We don't have class on Friday. I keep doing that. Exam one is going to be Wednesday. I guess that would be the 11th. And so on Wednesday, I'll tell you for sure what topics it's going to cover and stuff, but just so you know that that's on the way. Um, okay, so for number 10, it says there's this material sample. It gives you the starting dimensions. And it tells you how much the thing deforms, and you're just calculating Young's modulus and Poisson's ratio. We'll always use a coordinate system with the x-axis along the direction of loading. This is being put into 4,000 newtons of tension. Okay, so we'll first calculate the Young's modulus. So for that, we need the XX normal strain, which is the force divided by the cross-sectional area, and this is the cross-sectional area that we care about. So that has one dimension of 0.1 and one dimension of 0.008. So that's 5 times 10 to the 6. And then we need the XX normal strain. So that is how much it stretches divided by the original length. So to measure how much it stretches, that is 0.30015 minus the starting length divided by the starting length. That's 1, 2, 3, 4 zeros. So that is 5 times 10 to the minus 5. This stress is in units of pascals. And so Young's modulus is 5 times 10 to the 6 pascals divided by this unitless 5 times 10 to the minus 5. And I guess that's 1 times 10 to the 11th. And that's in pascals. And then for Poisson's ratio, we almost have everything we need. We just need the strain for one of those off-axis dimensions. We're given that the width that started out as 0.1 is now this thing. So that's point. Let's see, 0, 1, and then 1, 2, 3, 4, 5. So 0, then 5 nines, and then a 4 minus 0.1 divided by 0.1. And this is not the Poisson's ratio, sorry, this is just the off-axis normal strain. I'll call this EYY. So that is negative 6 times 10 to the minus 6. And so now the Poisson's ratio is the negative of the off-axis strain divided by the on-axis strain. And that is 0.12. Is that a possible value? It's possible. The possible values go from 0 to 0.5. We usually expect it to be closer to 0.3, but this is possible. Anybody have any questions about that?
What's equations will be like given on like the test? Like, are we given any equations?
Yeah. Yes. I guess on the test, I probably give something like this. Like for a problem like this, I would give something like this. I would give something like this. I would give that Young's modulus is equal to sigma xx over exx. I'd give Poisson's ratio is negative EYY over EXX, and that's also equal to negative EZZ over EXX. So I would give you all that stuff for a problem like this.
So basically, there's no like specific equations you require us to memorize. And our calculators, will we view out those? Like,
yeah, you'll be able to use your calculators. Yeah. I really don't think there's anything that I expect you to memorize. I don't think there's anything this whole semester, but if I notice anything like that, I'll try to let you know.
Well, that one has the matrix on our calculators
Yeah.
by the time the
Yep. But I definitely still give you like the whole form of the compliance matrix too, even though you probably have it entered in your calculators.
So we could do it by hand.
Yeah.
We probably wouldn't want to.
You do not want to. That I know from experience. Any other homework questions you want me to go over? Okay. Yeah. Okay. So the next thing I want to talk about is stress transformations. And the idea is that given a stress tensor in one coordinate system, express that stress tensor in a new coordinate system. And you're used to doing this with vectors. In physics 1, for example, when you did sliding objects on inclined surfaces, you changed the problem into a new coordinate system so that it was easier to do the math. So this is just a matter of doing it for tensors instead of vectors. So think of it as like it's the tensor equivalent um, of having a vector like this and in a coordinate system like this. The coordinates, the components are 7.66, 6.43, and in a coordinate system like this, the components are 10, 0. Okay, it's still the same vector, it's just you're expressing it in a different coordinate system, and we're going to do the same thing for tensors. Okay, so to do that, we're going to use rotation matrices. And we're going to do it axis by axis. So first, if you want to rotate a coordinate system, theta degrees, counterclockwise about the x-axis. Clockwise and counterclockwise get a little confusing when you're in 3D. So when I say counterclockwise, you have to be like looking, like the point of the axis has to be pointing towards you. You can also think of this in terms of the right-hand rule. But in order to do this, the rotation matrix Q is 1, 0, 0, 0 cosine of theta, sine of theta, 0 negative sine of theta, cosine of theta. Second, if you want to rotate the coordinate system, an angle theta counterclockwise about the y-axis, then the rotation matrix is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And third, if you want to rotate the coordinate system counterclockwise an angle theta about the z-axis, the rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. So notice the pattern here, like compare the X and Z versions first. The row and column connected to the axis you're rotating about is all zeros with a 1 in the, in that diagonal position. And then it goes cosine, sine, negative sine, cosine. The y almost follows that pattern, but the negative signs are switched because the y-axis always has to be a little bit cute, like with the cross product and whatever. The y-axis always has to be a little difficult, but it's always just changing a sign somewhere. So first, let's see how it works with vectors, because you can use these rotation matrices for transforming vectors to new coordinate systems too. So, okay, let's say that we have, this is the example I had before. Let's say we have a vector with a magnitude of 10, and we're going to start with a coordinate system like this. And let's say that the angle with the horizontal is 40 degrees. Well, you can see that that 10 just points straight along the positive x-axis. So in this coordinate system, that vector is 10, 0. And we want to know what are the components in a coordinate system like this. Well, you can tell from, like, if you just make that right triangle and do the right angle trigonometry, that's going to be, for an x-axis, it's going to be 10 times the cosine of 40. For the y, it's going to be 10 times the sine of 40. And so it'll give us 7.66, 6.43. So let's see that come out, and that's the one that's the example I did up here. Let's see that come out using the rotation matrix. So we want to go from this coordinate system to this one. So is that a rotation about the x, the y, or the z axis? Z. And is that, if you're looking straight down the barrel of the z axis, is that a clockwise or a counterclockwise rotation? That's clockwise, and so our theta is going to be negative 40. So our rotation matrix is going to be cosine of 40, cosine of negative 40. Sine of negative 40, 0. Then negative sine of negative 40, cosine of negative 40, 0, and then 0, 0, 1. And that comes out to be 0.766, negative 0.643, 0, positive 0.643, positive 0.766, 0, and then 0, 0, 1. And now we're just going to multiply. So our u vector in the new coordinate system is just this Q matrix. Times the original vector, the vector in the original coordinate system, which was 10, 0, 0. And you get 7.66, 6.430. Yeah. Okay, so with a tensor, so you can do the same thing with tensors. This time, the new tensor, the tensor in the new coordinate system, is equal to the rotation matrix Q times the tensor in the old coordinate system times the rotation matrix transpose. So why do we need two rotation matrices here? Well, basically what it's doing is one of them uh, puts the traction vectors on inclined faces, new faces. Remember that the way that you adjust the face of a traction vector is by multiplying the outward facing normal to the stress tensor. Remember, we did that last week or something. And so one of these rotation matrices is doing that. And the second one is re-expressing those traction vectors in the new coordinate system. And one thing to remember here, so what does that transpose do? Well, rotation matrices are a type of matrix called orthogonal matrices. So rotation matrices are orthogonal. So that means that the transpose is the inverse. So really that Q transpose is functioning as an inverse. Okay, so let's do some examples to sort of get used to how this works. So in this coordinate system, let's say that we have a stress tensor of 5, 0, -1, 0, 10, 0, -1, 0, 2 in megapascals. And check that real quick and make sure that's an allowable stress tensor. It's symmetric, so that works. And what we want to do is re-express this or transform it to a new coordinate system in a coordinate system where the x-axis is up, the y-axis is to the left, and the z-axis is out of the page. And then, is there a way to make physical sense out of this, intuitive sense? a way to make intuitive sense out of this. Okay, well, the first thing we have to do is we're talking about an original coordinate system like this. And a new coordinate system like this. So what axis are we rotating about? Z, and it's a 90-degree rotation, clockwise or counterclockwise? Counter, so yeah, so we're going positive 90 degrees about Z. On the last one, I don't know if I wrote this is about Z also. Okay, so let's fill out the rotation matrix. So Q is equal to cosine of 90, sine of 90, 0, negative sine of 90, cosine of 90, 0, 0, 0, 1. So that is 1, 0, 0, 0, 1, 0, 0, 0, 1. Nope, I did that exactly backwards. Sorry, erase all those. Cosine of 90 is 0. Sine of 90 is 1. So 0, 1, 0. And then negative 1, 0, 0. And then 0, 0, 1. Okay, so that's our Q. And so now we're going to go our stress tensor in the new coordinate system is Q. Times our old stress tensor, and you can do these rotation matrices in any units, so I'm just going to leave it in megapascals. 5, 0, negative 1, 0, 10, 0, negative 1, 0, 2. And then the transpose of this, so the first row is 0, negative 1, 0, then 1, 0, 0, then 0, 0, 1. Okay, so there's the answer after we transform this into the new coordinate system. Now part B says, can we make any intuitive sense out of this? Okay, well, in order to do that, let's think about the stress cubes. Okay, so okay, so first of all, here's the stress cube. It's in the orientation that we always draw the stress cubes. And the original says on the X face, we have a positive X component, no Y component, and a negative Z component of 1. On the positive Y face, we have nothing but a normal of 10. And then on the Z face, we have the 1 matching the 1 on the X face, and then we have positive 2 coming out. Okay, so this is the positive X face. This is the positive Y face. And this is the positive Z face. Okay, so now I'm going to draw the stress cube for the new coordinate system. Yeah, exactly, because it's all, I mean, normally these aren't rotated at 90-degree angles, but in this case, it's just a 90-degree rotation. So the cubes look exactly the same. And since the cubes look exactly the same, we expect to have the same tractions on all of those faces. Okay, it's just what face we're talking about changed. You know what I mean? So, so this time, so I'm going to draw this cube. And let's think about what faces are showing. So the positive Y face is obscured over here. So this one is the negative Y face. This one is the positive X face. And then this one is the positive Z face. Okay. And using the components that we calculated, on the positive X face, all we have is 10 in the positive X direction. Now go to the Y face. Well, the positive Y face is obscured, but that has a 5 in the positive Y and a 1 in the positive Z. But since what I'm drawing is the negative Y face, all those get flipped. So we have a 5 in the so we have a 5 in the in the negative Y direction, and a 1 in the negative Z direction. And now we go to the Z face, and all we have is 1 in the positive Y direction. Positive Y is to the left now. And 2 in the positive Z direction. And so you can see that those, even though the numbers, the components all changed, when you look at the stress cube, it tells the exact same story, which is what you expect because it's the same state of stress.
We're supposed to have X in there.
X now is the top face. And so that top face has to match our old top face, you know. Each face has to match the face on the old one. So like what's named what changed, some negatives changed, but you end up with two cubes that tell the exact same story. Okay, so let's do another one. So let's say we start with a stress cube like this. Um, and let's say we have 20 megapascals in the x normal direction, 10 megapascals in the negative y normal direction, and then 15 megapascals in the negative z normal direction. And we want to express this in a coordinate system that's rotated 45 degrees counterclockwise about the z-axis. Okay, so what I want you to notice about this is notice that there are no shear stresses in the original stress cube. Or so in the original stress tensor. So, okay, do you think, like, does your intuition tell you normal stresses and shear stresses are fundamentally different? So, if you have if you have no shear stresses in one coordinate system, you necessarily have no shear stresses in other coordinate systems? Or do you think they go back and forth as you do these rotations? You know what I mean? Yeah, I mean, I think that kind of would be my intuition too. But it turns out that what we're going to see is that we develop shear stresses when we look in a different coordinate system. Okay, so just keep that in mind. There's nothing like sacred about normal stresses, shear stresses. When you rotate this thing, they go back and forth. The same way just components go back and forth of a vector when you change to a new coordinate system. Okay, so let's see what happens here. Yeah.
The C force is negative 15, right?
Yeah. Yeah, I usually just write it as positive.
Oh, okay. Yeah,
You're
because
right.
the Y
Yeah,
value was pointing.
exactly. Yeah, I should write it like this. Okay, so our we want to rotate 45 degrees about the z-axis. So our rotation matrix is going to be cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45, 0, and then 0, 0, 1. So that's like 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1. And our stress tensor in the old coordinate system is 20 for x, 0, 0. Then for y, 0, negative 10, 0. And then for z, 0, 0, negative 15. So our stress tensor in the new coordinate system is equal to, I'll just write out the symbols. So we got Q times the stress tensor in the old coordinate system times Q transpose. 5, negative 15, 0, negative 15, 5, 0, 0, 0, negative 15. Bless you.
And after that, do we need to draw the new? Oh.
You could. By the way, so I did this one where we did the stress cube in sort of a funky coordinate system, but I'm never going to make you try to draw these at 45-degree angles or anything like that, you know. So if you drew this stress cube, I would just draw it with the x-axis, the direction you're used to, the y-axis, you know. But the key thing here is there were no shear stresses in the original coordinate system, and now there are. Okay, so things can go back and forth between shears and normal stresses as you change coordinate systems. In fact, this coordinate system that I chose is the one with the biggest magnitude of shear stresses that you can find anywhere. So there's, infinitely many coordinate systems you could try. And if you tried all infinitely many, it would take you a long time, but you would find out that you can't get any bigger absolute value of shear stress than this. Okay. And that's actually getting at a really important fact that you can think of it as kind of like, so there's a coordinate system where you have the biggest normal stresses, always for any state of stress. And there's also a coordinate system where you have the biggest magnitude of shear stresses. And those coordinate systems are really important for understanding the overall likelihood of fracture. Okay. So for any state of stress, there's a coordinate system where the normal stresses are biggest. And a coordinate system where the shear stresses are biggest. And these are important for understanding the material behavior. These coordinate systems are important for understanding the material behavior. And so that brings us to the next topic, which is principal stresses. Okay. Before I get into principal stresses, anybody have any questions about stress transformations?
There is any way can we do one where we think about the what?
Oh, yeah. So let's go. So let's say we're going to go from this coordinate system to one like this. Where the x-axis now is rotated back 20 degrees. The z-axis is rotated 20 degrees. The y-axis is still the same. So now this is the x, this is the z. And so our theta is going to be positive 20 degrees about the y-axis. So our q is going to be cosine of 20, 0, negative sine of 20. You have that funny negative in there. Then 0, 1, 0. And then sine of 20, 0, cosine of 20. And so that's 0.940, 0, negative 0.342, 0, 1, 0, positive 0.342, 0, 0.940. And then I'll just make something up for this. So let's say negative 2, 0, 1, 0, 5, negative 2, 1, negative 2, negative 10. Check and make sure it's symmetric. Everything goes haywire with these if it's not symmetric. And so then in our new coordinate system, it's going to be q times this times q transpose. And I get negative 3.58, 0.684, 3.34, 0.684, 5, negative 1.88, 3.34, negative 1.88, negative 8.43. And notice that, after you do this transformation, you get a symmetric stress tensor again. I mean, to be a valid stress tensor, it has to be symmetric. If you ever get a stress tensor in any configuration that isn't symmetric, something went wrong. Any questions about that? Okay, so now we're going to use this idea with principal stresses, this idea that for any state of stress, so the state of stress is like a physical thing. You can't change that as a mathematician, but you can look at it from different coordinate systems. Like think of it as looking at it from different angles, and you get different numbers. The same way that you do with vectors, you look in a different coordinate system and the components are different. And the idea of the principal stress is this. It's actually pretty amazing that this is true. For any state of stress, there is a coordinate system with no shear elements, or with no shear stresses. We saw that when you change the coordinate system, normals turn into shears and shears turn into normals and all this stuff. But no matter what stress tensor you start with, there's some coordinate system where you can look at it where there are no shear stresses. Okay, all you have is normal stresses. And that's called the principal stress. Well, that's called the principal coordinate system. And the corresponding stress tensor is called the principal stress. Okay, that's kind of amazing enough. I mean, like, there's nothing that would pop into my head to make me think that that this would be possible in every case. But no matter what stress tensor you start with, there's a coordinate system somewhere where there are no shear stresses. But there's more kind of amazing stuff. And the greatest normal stress possible is in the principal stress, the principal stress tensor. That's kind of amazing. And there's one more thing. There's really two more things, I guess. And the minimum normal stress is in the principal stress tensor. And this is the last one. If you rotate the principal coordinate system 45 degrees about the middle stress axis. Don't worry too much about what that means just this second. The new stress tensor has the maximum possible absolute value of shear stress. Okay, so for this one, see the example that we just did? So I'll talk about that for a second. But the bottom line is by finding this principal stress, finding this principal coordinate system, you can identify the biggest, the maximum normal stress, the minimum normal stress, and the maximum absolute value of shear stress. And those are all really useful things for predicting fracture. So let's look back at the example. So what we did in this one, I started with, notice that I started with a principal stress tensor. I started with a state of stress where there were no shear stresses. I identified the middle, no, I didn't. Oh, well, what I said here is wrong. But so what if I had identified the middle of these three normal stresses? So our normal stresses are positive 20, negative 10, and negative 15. Okay. So now if I would have rotated the coordinate system 45 degrees about the middle of these axes, which is the one with the negative 10, I would have gotten a maximum possible value of shear stress. I think I did it about the z-axis instead of the y-axis, so I didn't do it.
What is the difference?
With what?
If you rotated about the y and
Okay, because the y-axis is the one that has the middle of those three values. Our normal stress values are positive 20, negative 10, and negative 15. This stress tensor is, just look at the diagonal here, 20, negative 10, negative 15. So if I would have rotated 45 degrees about the axis with the middle one, which is y, I would have gotten the maximum possible shear stress value.
so you mean by the middle, like the axis? The middle axis?
Yeah, so you're always going to rotate 45 degrees about one of these axes. To find which one of those axes to rotate about, you just have to locate the middle of those three normal stress values.
So the 15 is in the middle.
Right, that's the minimum value. Just like put these in order. From maximum to minimum is 20, negative 10, negative 15. So the middle one is negative 10. Okay, where did I put that thing? Okay. Let's stop there. And then, so on Wednesday, we'll get into doing calculations of the principal stresses. Yeah. Okay, goodbye.